Swayam Prabha. Digital India. Educated India.
Okay, any suggestions from anybody? Yes. Okay, can you say A1 to B2, A2 to B1, A3 to B3, A4 to B4. Okay, so she has given us this assignment, which is a valid assignment, and just to make sure that we are. So now let us all verify whether this is a stable matching, right? So she has proposed that this is a stable matching. She has given this output. So if we were to verify that this is a stable matching, we first look at A1 and say that A1 cannot participate in a blocking pair because it is assigned to its best partner. A2 can possibly participate in a blocking pair with B3, right? So we look at B3's preference list and check this edge A2 B3, right? So B3 is assigned to A3 and it prefers A2 worse than that. Therefore, this assignment is this doesn't form a blocking pair, and after this A2 cannot participate in any other blocking pair. Now we look at A3. A3 is assigned to B3 and A3 prefers B2 over its current partner. So let's look at B2's preference list. B2 is currently assigned A1 and we look at B2 A3. So what do we see here? B2 A3 is indeed a blocking pair with respect to this assignment. So therefore this matching doesn't stand its test for being a stable matching because we have identified one blocking pair. Even if rest of them are not blocking pairs, this is not a stable matching, right? It's a good attempt, but it unfortunately is not a stable matching. Anybody else has? Okay. So maybe somebody who has not answered, yeah. Or maybe you have not answered, yeah. Okay, let me just erase this. A1 to B3. Okay. A2 to B1. A3 to B2. A4 B4. Okay, so now I will let you verify whether it is a stable matching. A1 is, sorry, okay, A1 to B3, right? It is stable. Okay, so let's verify A1 B2, it can participate in the blocking pair A1 B2, but B2 is matched to B2 is matched to A3 and it, okay, so A1 with B4 is matched to A4, this is A1. So what about this pair A1 B4? So A1 is matched to B3. So A1 would like to get assigned to B4. and B4 is currently matched to A4 and it prefers A1, right? Therefore, this matching is blocked by this pair which is A1, B4, right? So this also unfortunately is not a stable matching. So after these many tries, one may start feeling that there are systems where there is no stable matching, but indeed we will illustrate using another matching that this instance does admit not only one but two stable matchings. So A1, B4, A2, B3, A3, B2 and A4, B1. Right? So I'll leave it to you to verify. Unless you show me a witness blocking pair, I will say that this is a stable matching, because I have computed it. So can anybody spot a blocking pair or an unstable pair? So it's not difficult to verify, because anyway you just have to verify A1, B2 and A4, B4, right? These are the only two possibilities for being a blocking pair, and both of them are not blocking pairs. Therefore, this indeed is a stable matching, right? So at least this instance that we have written down, this preference system does have a stable matching, right? But before we go to, so what I will write down, so this stable matching can be conveniently written without this graph, and what I will write it as a collection of edges, and I will call it M1, which is A1, B4, A2, B3, A3, B2 and A4, B1, right? And M2, which is, so now I am going to write another matching which you can again verify that that is also a stable matching, which I'll quickly write down. So A1, B4, so A1 retains its partner, A2 gets, instead of getting matched to B3, it gets matched to B1, A3, B2 and A4, B3. Right? So in these two matchings, one thing that we observe is A1 and A3 have retained their partners, and A2 and A4 have switched their partners, and it's a different matching, right? So these two are different matchings, we'll call them M1 and M2, and it is easy to verify that both these matchings are indeed stable. So what this shows is that at least this instance admits not only one but two stable matchings. So in particular, the stable matching need not be unique, right? But we tried by hand by doing some permutations, and we found that it was difficult to compute a stable matching by just inspection. So there we should ask, is there a systematic way or an algorithm which we can apply to get a stable matching if it exists, and say if it doesn't exist, right? So this is what we would be interested in. Before we go there, let's ask one simple question. Whenever you gave me stable matchings, all of them had size 4. That is, they were indeed, you were proposing matchings which had size 4, whether they happen to be stable or not. But do you think that there can be a stable matching of size 3? In a bipartite graph where there is complete bipartite graph, there are all edges. So let's say that I indeed have a matching which has only 3 edges. So these 3 edges, I am drawing them horizontal, but in particular they can be in any way. So what does this mean? That there is some AI and some BJ both of which have not been assigned to anybody, and in particular not to each other. But what do we know about their edge between them? That edge is present in the graph because every AI has listed all of B1 to Bn and every Bj has listed all of A1 to An. Now, what we did not do in this definition that we had is, we will say that a pair AB is unstable or blocks M if AB does not belong to M, which this edge satisfies. And then we say A prefers B to its current partner in M. In fact, it doesn't have any partner in M, and we very ahead of time said that any participant likes to get matched over being unmatched. So we will say that, in fact, one should say either A is unmatched in M, because this statement A prefers B to its current partner is valid only if A is matched in M, right? Therefore, if A is unmatched, it certainly prefers anybody over its unmatched partner. Symmetrically, it applies to B, that is either B is unmatched in M or B prefers A to its current partner. If this happens, we will call that as a blocking pair. So, in fact, now this AI Bj is an edge which is a blocking pair with respect to this 3-sized matching. And in fact, if you have any 3-sized matching where you have a complete bipartite graph, it will be a matching which will be blocked by that edge. Therefore, what this tells us is that if there is a stable matching, all stable matchings must have size n or 4 in this example. That is, if it is an n cross n system, then it has size n, right? It cannot be smaller than that size, else there is an edge which will block that matching. Everybody with me? Okay. Okay, so what we have seen is what is a stable marriage instance or a stable matching instance. We know how to specify the instance. For now, we are talking about n cross n systems where there are n men, n women. Each man has a preference ordering over the women, and vice versa. We have also seen the definition of stability. That is, we know, given a matching, how to check whether it is stable or not, right? What we will be interested now is to compute a stable matching. If it exists, right? So this is what we will give or present an algorithm for. And this is a very classical algorithm which is given by two prominent researchers, Gale and Shapley, in 1962. And as I said, while they made this study very formal and they gave, they formally wrote down the algorithm, a variant or a similar algorithm was already in place in the National Residency Matching Program prior to this in the US. And they were already following this without mathematically studying the properties of this algorithm, the problem and so on. So what this algorithm suggests is very intuitive, that is, in fact, it does exactly what our algorithm did earlier, that is, let's look at it from the men or the student order and start applying or assigning the students to the most preferred program or most preferred women that is currently not yet occupied, right? So that goes on well as long as there is no conflict. So if you recall in our example, A1 assigned to B2 was fine, A3 assigned to B3 is fine, A3 when it is trying to get assigned to B2 or apply to B2, there is where the problem stems in, that is, we did not do anything, we said that okay, since this is not free, we go down. So here is where the algorithm deviates, and we will instead of writing the algorithm formally first, we will try to see what the algorithm does. So we will call this a sequence of proposals, and this A1 proposes to B1, B2, which is the top choice in his preference list, and currently because B2 is unmatched, therefore she is going to say that yes, tentatively I will say that this is my current partner, right? So this we'll use a tick to show that this proposal is accepted. Now A2 goes and proposes to the first person on the preference list, which is B3, and because B3 is also unmatched, to begin with all A's and B's are unmatched, so this also goes through. When A3 proposes to B2, now instead of saying B2 is matched, B2 now evaluates this proposal, and B2 looks at the preference list and sees that currently she is tentatively assigned to A1, whereas she is getting a proposal from A3, which is a better preferred person. Therefore, instead of rejecting this person or rejecting this proposal from A3, she will accept this, but of course her capacity is 1, that is she cannot accept more. Therefore, in fact, she rejects this proposal, that is this is no longer a valid partner and this proposal is gone. At this moment, A1 is no longer assigned to anybody and A1 is free, right? So now we have two people who are free, A1 and A4, and we can take, we will see, we'll just go in the order. So we'll go in A4, and A4 proposes to B4, and because B4 is again free, therefore it is going to accept it. Now A1 is free. Is there any point in A1 making a proposal to B2? There is no point, because that was where it got rejected. Even if it makes a proposal, it is going to get rejected because B2 is going to retain the better of the two. Therefore, A1 will propose to the most preferred woman on the preference list, to whom he has not yet proposed, which happens to be B4. So think mentally that there is a current pointer in the preference list and it is going in that order. So A1 proposes to B4. Now again there is a conflict because B4 is not free. So B4 is currently assigned to A4 and A1 is proposing. What should it do? It should reject this assignment, that is this will go away, and A1 will get accepted, right? Now again this leaves A4 unassigned or unmatched. Now again A4 has no incentive to go and propose to B4, therefore it will go and propose to the most preferred woman whom he has not yet proposed, which is B1, and we will get a proposal A4 B1, which, because B1 is still free, it will accept it and this proposal gets accepted, and currently we have a matching which is of size 4, which is A2 B3, A3 B2, A1 B4 and A4 B1, right? In fact, this is what was the matching that I presented to you, which you verified that this is a stable matching, right? So now what we will write down is a clear algorithm in terms of a pseudocode. That is, when we are given an n cross n bipartite graph with preferences of the A's and the B's, we will run this algorithm and we will prove some properties about the output of this algorithm, right? So this is called the Gale and Shapley algorithm. So set all A's and B's unmatched while there exists an unmatched A. I did not write this as two sets, but we can write them as the two sets A, B, and therefore the graph, bipartite graph, is A union B, and the H set, which is the complete, each AI has. So while there is an unmatched edge, unmatched vertex A belonging to A proposes to the most preferred woman B on A's list to whom he has not yet proposed. And this can be conveniently maintained by keeping a pointer where should you next propose if this gets rejected. So A proposes to the most preferred woman B. What can be the two scenarios for B in a general execution of this algorithm? B can be either free or unmatched, or it can be matched. So if B is free, then A, B is tentatively accepted, or then we'll say B tentatively accepts A. And why do I say tentatively? Because if B gets a better proposal, she's going to reject the proposal from A. Else let A prime is equal to M of B. Recall this notation. We said that so there is a current matching that we are maintaining, M, which is empty. So I could have also said M is equal to phi and then add AB to M. So there is a current matching that we have. So if it is not free, then it is matched. Therefore, it must be matched to somebody. Let's call that partner as A prime. So the picture is like this. B is currently matched to A prime and B gets a proposal from A. So at this point, what is B going to do? It is going to evaluate the proposal based on the preference list. So if B prefers A over A prime, then M, which was the current set of edges which were matched, if B prefers A, then it is going to delete this edge, that is M minus A prime B and then union AB. That is, it has removed this edge, removed this engagement or matching and added this edge AB to the current matching, and this is depicted by removing this A prime B and adding this AB, right? So this is what happens. Else if B prefers A prime over A, we don't do anything and A remains unmatched. That is, A will now move its pointer from B to the next person to whom it has to propose. It is as good as B has rejected the proposal of A. Else B rejects proposal of A and moves forward. I won't write that, but there is a pointer that we are maintaining. So this algorithm is what we will execute or run, and this is called the Gale and Shapley algorithm. We will want to ask certain properties about this algorithm, but as a very first property, is it even an algorithm? That is, does it even terminate always? Because it seems to start with everybody unmatched, then some people get matched, then some people again become unmatched. So maybe it goes on in cycles and never terminates. So can this happen? That is, it doesn't even stop, it keeps on executing because it's just switching between these assignments and then again undoing them, redoing them again and again. If it happens, then this is not a good procedure to follow, because for some examples it may go on forever. Thankfully for our example, it did not happen. So can it happen that the algorithm keeps going forever? So in this example, we had a finite set of proposals and it stopped after that, at which when no man is unmatched, we have stopped that algorithm. That is where the while loop stops. Any thoughts about whether it will go on? How many of you think that it will terminate? How many of you think that it may go on some examples? So let's see how many of you think that it will terminate, that will always terminate. Okay, you think that it will always terminate. So everybody else thinks that it can go on forever, right? Very good. So this is, maybe this is carved so that it terminates, right? But there may be some examples where it doesn't terminate. So we have a nice coffee break where you can generate an example where it does not terminate, and we have one contender who says that it will terminate. So there we need a proof that it will terminate, right? So maybe some people will switch sides, but let's see. So when we come back, we will see whether somebody can give us an example that it doesn't terminate, or somebody can give us a proof that it terminates. We'll stop here now.